Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Boom. Boom. Some people are still coming in. All right, let's jump into it. Okay, I'm seeing you guys. I'm seeing me. I'm seeing the chat. All right. Okay, so let's jump into it. We have a few examples to get through with L'Hopital's rule, and we will also, I guess, at least start a new topic. Maybe that's the plan. We'll see how far we get. Just one important announcement before we begin. I sent out an email yesterday, I think it was, maybe the night before, but recently I sent out an email about moving the next quiz to the following week. That's because this week coming up, it's like Easter Sunday or something. So far, no one has complained about that. So I'm just going to assume moving forward, that's what I'm doing. So your next quiz is the week of the 11th. It'll be on the same topics. The quiz is going to remain the same. It's just I'm going to give it a week later. That's all that's going to happen. So just so you guys know. Yeah, with that being said, let's actually just move on. So we went back to limits because we want to talk about a new special technique called L'Hopital's rule. For that, we needed to discuss things called indeterminate forms. Now, these were limit forms. These forms arise when you're taking limits because, of course, infinity doesn't really arise from some computation. But it arises when you're taking limits. And they are forms in which you cannot really determine them at face value because of the competing ideas that they espouse. It's more that they can be interpreted in multiple ways that would give multiple different answers, and you can't be sure which is which or what part of the expression would win, etc. There are a few times you can, as with our first two examples, where we had indeterminate forms for e to the x over x as x goes to infinity, as well as ln x over x goes to infinity, but we had another strategy that could work there. But we are introducing a new strategy called L'Hopital's rule, and basically it works on these two types of indeterminate forms specifically. So it works on these guys over here. It does not work in general whenever you want it to. Even though it's pretty cool and you'd want to apply it everywhere you can, you cannot apply it everywhere you can, everywhere you want to. It only applies to these two special situations. Now, of course, chances are we can rewrite these situations. So we can use L'Hopital's rule or something else. Of course, using algebra, which we're all experts on. So sometimes it's possible to rewrite these scenarios into a useful scenario where you can actually apply L'Hopital's rule or something else, some other concept. But for the most part, these guys are indeterminate. You can't determine them at face value. And L'Hopital's rule helps with the first two, the last two that I listed here. So suppose you're taking the limit of a division of functions, and that limit approaches 0 over 0 or infinity over infinity with whatever combination of plus and minuses. Then it turns out that you can differentiate the top and differentiate the bottom. And as long as the original limit exists, this new limit will actually give you the same answer. You can do this repeatedly as often as you want. And I would recommend that you simplify between each application, because you might notice that after applying L'Hopital's rule once, you might think you need to apply it again, but you probably don't. If you just simplify it algebraically, you'd realize that, oh, I can determine the answer now. We had 7 examples to go through. We already went through two of them, two of the easy ones, the ones that we could have solved prior to knowing about L'Hopital's rule. And now we're going to solve the others, right? So we solve these guys here. Notice that they give you infinity over infinity. As x goes to infinity, e to the x goes to infinity, and x goes to infinity. So you have the L'Hopital's rule, which we indicate that we're applying L'Hopital's rule by writing that over the equal sign to say that this equal sign follows from L'Hopital's rule. And yeah, after that, we could tell the answer pretty easily. But we could actually know what the answer was because it was top heavy. This one was bottom heavy. We should have known the answer was 0, but just as an illustration of L'Hopital's rule and the fact that it will give us the same answer, we applied L'Hopital's rule and we got 0 as well. Now let's move on to the others. Content not yet available. Why is that? Okay, not sure what's going on there. I'll have to fix this later. 1203 dash R, I want to say 04. Dash, and it's 3:30:21. I think I can't select that for some reason. I don't understand why I can't select that. Oh, never mind. I think it's loading now. Oh, iPad. All right. Let's go back, do these guys. Well, I mean, I'm seeing it on Zoom, so I'm definitely connected to the internet. Why won't it load the page? I don't know. Not gonna work for it. Wait on that. Okay. We already did this and this. So let's do the others. So C, the limit as x approaches 0 of x ln x I really can't get into these Apple products, man. People always like recommend them to me. Oh, it's the best. You should definitely get an iPad. It's like, I fail to see how people find these things productive. Like, I don't, like, what are you doing with your life if you think like an Apple product is like productive? Anyway, notice here that technically we have an indeterminate form. If we were to look at what this limit is behaving like, as x approaches 0 from the right, the x would approach 0, and the ln would approach negative infinity. Right? So we have a 0 times infinity indeterminate form here. Okay, so what can we do here? You guys tried. How would you continue? Ideas for what we can do? Zero times infinity. How do we fix that?
The reciprocal of x. So 1 over x times ln x.
You could do that. So here we could have ln of x divided by 1 over x, right? Now, of course, dividing by 0 would be an issue, but we're not at 0. We're approaching 0. We're getting close to 0. So since 1 over x is the same as x, I could rewrite one of these guys. I could also write it as, 1 over ln of x, 1 over ln of x. But now notice that I have a division. So now, maybe I'll put that note here. Since 1 over x equals x, this equation follows. And now you can notice, now we have, as x approaches 0 from the right of ln, ln would approach negative infinity. As x approaches 0 from the right of 1 over x, that would also approach infinity. That would approach positive infinity. So here we have an infinity over infinity. This means L'Hopital suddenly applies just by me rewriting. So what, according to L'Hopital's rule, L apostrophe H, L'Hopital's rule, you have to say it in the French accent or it might not work. We can just differentiate the top, differentiate the bottom. Derivative of ln x is 1 over x. Derivative of 1 over x is minus 1 over x squared. Right? Now, you might be tempted to see that, well, I mean, this is going to be infinity over negative infinity. But if you do that, you shouldn't do that. Always simplify before considering L'Hopital's. Again, so instead of looking at that as another infinity over infinity, I guess I'm going to have to do it again. Because what you're going to realize is that you would have to do it again and again and again and again. And it's like, oh my God, this is never going to end. However, if you were to just stop and simplify, you'd realize that you end up in a very different situation. Here, you keep change flip. So that is going to be the limit as x approaches 0 of negative x, which is super clear. That's not indeterminate. I know what that is. That is 0. Okay, so I only need L'Hopital's rule once here. You may not have noticed that if you just decided to go into L'Hopital's rule again. As I said, you don't just randomly apply strategies. You deliberate a little. You think, is this strategy worth it here? Can I simplify first, right? Apply the lower level rules first. And you realize this is 0. Now, the idea is, again, because polynomials move faster than logarithms. So when x is approaching 0, it's approaching 0 a lot faster than the ln x is approaching infinity, is kind of the idea. And so overall, the 0 would win instead of the infinity. And in this case, it turns out to be 0. That doesn't always happen, though. It could have turned out to be something else. But yeah. D, x to the x. Limit as x approaches 0 from the right of x to the x. Approach 0 from the right because I don't want to have to worry about complex numbers. If the base is negative and then the power is like a half or something, I don't want to have to skip over complex numbers. So we have that, right? Now, if I look at what this looks like, x is approaching 0. What is happening to the base? Well, it's 0. And the power, well, that's 0. That's 0 over 0. This is an indeterminate form. You cannot use L'Hopital's rule, though. Hopefully you recognize that. But this is an indeterminate form where the issue is the power. Base 0 to the power 0 is a problem because of the power 0. As long as the power is positive, 0 raised to a power is 0. That would be determinate. It's indeterminate because of the power itself is actually 0. So what do you think we can do when the power is an issue? How do we deal with things when powers are issues?
Logs.
Logs. You want to introduce a log somehow, right? Now we have a couple ways to do this, but my preference would be the way that I showed you towards the end of last class, how to actually introduce a log by rewriting stuff on the spot. So I would say this is e to the ln of x to the x. See, I can do that because my x's are positive. This is the same as the limit of e to the x ln x. And we know that this is going to be e to the limit of x ln x. Now this is because limits pass through continuous functions. We spoke about that a long time ago, continuous functions. So whenever I introduce a logarithm in this way, I can just focus the limit on the power, right? So here I'm rewriting. And now the limit is on the power. Now, you'll notice that that limit was the limit that I asked you to do last time. So we actually already know the answer. We already know the answer is going to be 0, but we know the power goes to 0 from the last example. But let's just do this example completely anyway, because I want you to see me applying L'Hopital's rule in the power. Okay. So what you're going to notice is that you now have e to the limit of x approaching 0 from the right of x ln x. right? What you're going to do is now notice that you can focus on the limit in the power. And so this, and so in the power, notice that this is approaching 0 times infinity, negative infinity, in fact. And so I realize that's an indeterminate form in the power. So now I want to try to rewrite it, do something else, try to get something going here where I can apply L'Hopital's rule or maybe something else. And that's when within the power, I would have changed it. Well, this is ln x over 1 over x. And we're still rewriting. At this point, I notice that the power goes to infinity over infinity, negative infinity over infinity. So now I realize L'Hopital's rule applies. I go, okay, let's apply L'Hopital's rule. And so now I have 1 over x over minus 1 over x squared. And this is going to be e to the limit, keep change flip, minus x squared over x, or e to the limit as x approaches 0 of minus x. And so I get e to the 0, which is 1. So as we have x over x raised to the x approaching 0 from the right, we end up with 1 as the limit. But it was an indeterminate form. I mean, there are a couple things that I wrote here. So, I mean, you could skip this line, could skip. You could also skip this line. Like you didn't have to write it out. I repeated this line, so you could skip this line. I would write that line, and the rest of it would be what I would write. So if you were writing out a full answer, you could have skipped those lines right there. Another way is to do it the old way that we did log differentiation. Set y equals this limit. Then you can introduce the log by logging both sides. So then this is the same as the limit as x approaches 0 from the right of ln of x to the x. Again, since limits pass through continuous functions, I can shift the limit in and out of the ln. And so now I actually have exactly the limit that was in the previous example. I would move that down to be x ln x. I would rewrite it as ln x over, say, 1 over x. I would then apply L'Hopital's rule to get 1 over x divided by minus 1 over x squared. I would then rewrite that. Which is 0. Now, a lot of students make the mistake when doing this, which is again why I don't like this cumbersome way of doing it. I much rather rewrite on the spot. A lot of students will see this and think the answer is 0, forgetting that they just computed ln of y, not y itself, right? So what we were computing now was ln of y. So really, ln of y is that, which means my y is actually e to the 0. So my y equals 1. The limit is 1. Right? This is one of the reasons why I prefer writing it on the spot. So you never actually forget this last step, which I see students forget every now and then, which is completely understandable. You're on a test, you're rushing for time, you're just not thinking. You've been working on the right side by itself for so long that you just forgot what the left side was doing. So that it happens all the time. To prevent that from happening, rewriting on the spot is going to work. You immediately introduce the e to the blah. So you're never going to forget to actually put the e back in the blah because it's been there the whole time. Yeah. Okay. Done that, done that. Let's do this one. E limit as x approaches infinity of 1 plus 1 over x to the x. Yes. Does anyone remember where this is from? Or what the answer should be? Because this approaches 1 to the infinity, right? As x approaches infinity, 1 over x approaches 0, so the base will approach 1. And the power is x. As x approaches infinity, the power is approaching infinity. So this approaches 1 to the infinity. Is the answer 1? Or is the answer infinity? Or is it something else? Does anyone remember this expression? Actually introduced it a long time ago. At this point, I don't even remember. Lecture 2 or 3 maybe. And we're like on lecture 22 or something now. So this was one of the definitions of E, right? Where I reminded you that E came from us looking at the compound interest formula and just imagining that we're compounding an infinite number of times per year at 100% interest rate. And when you plug in the compound interest formula into that kind of scenario, you get this kind of expression. And Euler, for who the number is named, figured out that this approached the number E. So this is actually E, right? It's not 1, it's not infinity, it's not a random number in between. It's actually the number E. It's 2.71828, blah, 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 right? So yeah, indeterminate form, you can't determine it at face value. So don't just think, oh, it's 1 to the infinity, it's probably 1. No, it's not. It's not anything close to 1. However, the power is an issue here. So I would do the same thing. I would rewrite this. Using E to figure out the definition of E. How meta. So this is ln of 1 plus 1 over x to the x. This is e to the x ln of 1 plus 1 over x, so it's no longer a power. Now I look at the power, look at what it's behaving like. Well, it's behaving like infinity times 0, which is also indeterminate. But not conveniently so. Not convenient. It's not conveniently indeterminate. Because this approaches x times log of 1, where the x is approaching infinity. So yeah, log of 1 we know is 0. So this is 0 times infinity. I would actually do a very similar thing as we did in the last couple of examples. Take reciprocals. So this is ln of 1 plus 1 over x over 1 over x. So I'm rewriting. Now I realize that this approaches, well, as x goes to infinity, 1 over x goes to 0, so the inside goes to 1, log of 1 is 0. As x goes to infinity, 1 over x goes to 0. So that is also an indeterminate form, and moreover, L'Hopital's applies. L'hôpital. So I'm gonna do that. L apostrophe H. Notice that I just wrote that on the equal sign because I've not applied L'Hopital's rule until this point. Everything else I was doing was just a simplification, a rewriting, a restating of what I had. But at this point, I'm in a position where I can use L'Hopital's rule because I have that 0 over 0. So what I would have now is the limit as x approaches infinity of e to this derivative of ln of that thing is 1 over that thing times the derivative of that thing, u prime over u, minus 1 over x squared. The derivative of 1 over x is minus 1 over x squared. You will notice that these two guys cancel. And so I end up with the limit as x approaches infinity of e to the 1 over 1 plus 1 over x. And now I sort of look at, well, what does this behave like now? Well, x is approaching infinity, so 1 over x is approaching 0. This is approaching 1 over 1, which is not indeterminate. That's like a number. I know what that is. Right? So this just approaches e to the 1, or in other words, e. E is the answer. And by the way, this is a definition of E. It's the definition that, no, I shouldn't say that calculus people like. There's a better definition that you would learn in Calc 2, but most of you aren't going to Calc 2, so never mind. So it's one of the first definitions to appear. Maybe I can say it that way. But we got a better definition in Calculus 2 with the use of series, and most people think of E by that definition now. But this is one definition of E. Let's see. That was example E. The answer was E. Let's go to example F. E to the x minus x as x goes to infinity. As we're on an iPad, it's easier for me to just write it down instead of just like copy it. So, yeah, as x goes to infinity, e to the x goes to infinity. And as x goes to infinity, x goes to infinity. So this is infinity minus infinity. It's indeterminate. But it's not convenient. Also inconvenient. So, yeah, how can we rewrite this? So one thing is, we already saw a trick that how we can go from a multiplication to a division by the use of reciprocals, and then that might put us in a position to leverage L'Hopital's rule. Here we have a subtraction though. How do we get the subtraction to go to a division? Well, one thing we can do is to first turn the subtraction into a multiplication and then go from the multiplication to the division. That could be something that could work. So probably the question I should ask you guys is, how do you go from something like a subtraction to a multiplication? Right, you have a sum. How do you turn it into a product? You have a process for doing that. What is the process for taking a sum of terms, then contracting them into a product, like one multiplication? What is that called? So here we have a sum. we'd prefer a division. We know how to go from division, multiplication to the division. As above. And believe it or not, we also know how to go from sum to multiplication. This is a process called, very strange name, not sure if you guys ever heard of it. It's called factoring. That's literally what factoring is going from a sum to a product. So example, if I have x to the x squared minus 4, that is x minus 2 times x plus 2. Notice that what I had here is a sum, and what I have here is a product, right? Factoring is a nice way to go from sums to products. So that's what I would do. I would try to factor. So for the limit as x approaches infinity of e to the x minus x, how can you factor this in a convenient way? Now, another thing that students often miss in math class is that they always believe that you have to factor out a common term. So I have to like have a rule like difference of squares, or I have to see the same term in everybody in order for me to factor out. This is not true. Those things make things convenient, sure, but you should be aware that at any given time, you can literally factor out anything other than 0 itself. So you can factor out any non-zero number at any point, at any time, for any reason that you feel like. Factoring out means it's essentially, if you want to break it down to its fundamental components, it's essentially like multiplying and dividing by something and then moving it out. So, for example, if I wanted to factor x squared minus x, why the common terms example works is I could have done this, like backwards, or let me maybe say, give me the real scoop. What really happens when we factor? Essentially, factoring means I multiply and divide by a convenient thing and then move the division part inside the parentheses. What really happens is I would multiply by x over x. And then what I would do is I would leave the x outside here and bring the over x inside. This would, of course, leave me with x in the first position and 1 in the second position, right? And this is why we subtract the powers of the things we move out, because it's a division and the laws of exponents apply. It's also why you always factor out the lowest power, because a convenient thing to multiply and divide by is always going to be the guy to the lowest power. So you can move it in and you would create like whole number components by dividing by the guy with the lowest power. If I multiply by x squared over x squared, then I would end up with a 1 over x inside the parentheses, which doesn't look very nice, right? So when we went from, normally we're used to jumping from this to that because of common term, but the reason why the common term idea works out is because of this. It turns out the common term is a convenient thing to multiply and divide by and slip in the denominator on the inside. So it's actually a way to rewrite a sum as a product. And so with that idea, you should be aware that we can actually factor anything out of anything. So similarly, we can factor anything except 0 out of anything. Why except 0? Because of the division that happens here. You can't divide by 0. So I can't go 0 over 0 and then bring in the 0 in the denominator. That's very illegal out of anything. So I can have ln of x plus e to the x, and I want to factor out x. I can do that. This is just going to be x times ln of x over x plus e to the x over x, right? I factored out x. Right? But x wasn't a common term. Doesn't matter. I can factor it out if I wanted to. All I did was multiply and divide by x and move the denominator on the inside. That's what we're going to do here. So that's another simplification trick. Here I have the limit as x approaches infinity. I can factor out an x. I would have e to the x over x minus 1. Now, I know that the limit of a product is the product of limits whenever the limits are finite. But at this point, they're not quite finite. They're infinite, but they're conveniently infinite. Notice what is happening here. We use L'Hopital's rule on this, shows this is infinity. That was actually our first example, e to the x over x. I didn't do it on this page, so I'm going to go back. So I know that that's going off to infinity, which means this whole parentheses here is going off to infinity. X, as x goes to infinity, is going off to infinity. So here I have infinity times infinity. Is that indeterminate? Can we know what infinity times infinity is? What is infinity times infinity? It's not indeterminate. It's actually just infinity. This guy here is not indeterminate. There are no competing ideas here, right? It's very clear. You take one huge number, multiply by another huge number, you get a huge number. There's no arguing. There's no question about that. The answer is infinity. Again, you can kind of realize that this was the case because the exponential grows a lot faster than the polynomial. As x is approaching infinity, the e to the x is going to overwhelm the x. So you're going to have an infinity minus something that's also infinity, but a much smaller kind of infinity. At any given time, when your x is super huge, your x is going to be very small compared to the e to the x. So it's also as if you can just sort of ignore this subtraction. It's not even going to matter. And infinity would be the answer. Where else are we? G, 1 over ln x, 1 over x minus 1. Double check that. X approaches 1 from the right, 1 over ln x minus 1 over x minus 1. Okay. All right. So we have this one. This is approaching, as you approach 1 from the right, ln of that goes to 0 from the right, from the left. So this is approaching as I'm approaching 0 from the right. So this is approaching infinity in the first case. As I approach 1 from the right, which means I'm 1 plus a little bit. If I subtract 1, I get a little small positive thing, but it's going to 0. So it's infinity minus infinity. At this point, you might be tempted to say that, oh, well, judging by what's been going on so far, the infinity at the second term is bigger than the infinity at the first term because the polynomial is going to move faster than the logarithm. So the second guy is going to go to infinity faster than the first guy, and therefore it's probably negative infinity is the answer. Because similarly here, infinity minus infinity, I kind of came up with the argument, well, the e to the x is going to be a bigger infinity faster than the x, and so maybe it's going to be infinite. However, this example will show us that this is truly an indeterminate form because the answer is not negative infinity. It's not infinity either, by the way, and it's not zero. So all the guesses that someone would typically make that would make sense at face value don't make sense here. And that is the point. I do not want you to assume anything when you're doing these guys. You just follow the process. What will the process actually look like? So here we have infinity minus infinity. Not convenient. However, I have two fractions. It might be useful to combine the fractions because then I get one big fraction. Maybe it might look like something that L'Hopital's rule could work. So here, this would be x minus 1 minus ln x over x minus 1 times ln x. All right, as x approaches 1, what happens to the numerator? 1 minus 1 is 0, minus ln of 1 is 0, you get 0. As x approaches 1, what happens to the denominator? X minus 1 is 0, log of 1 is 0, that just becomes 0 times 0, that's 0. L'Hopital's applies. L'Hopital's rule applies. So let's take it to the hospital. Find the derivative of the top. Derivative of x is 1. Derivative of ln x is 1 over x. Find the derivative of the bottom. I would need the product rule. So that's going to be ln x plus x minus 1 times 1 over x. Now I'm going to simplify before hitting it with L'Hopital's again, maybe, if I even need to. So we know how to simplify this. Multiply and divide by the LCD is the quickest way to simplify a compound fraction. So that would look like x minus 1 over x ln x plus x minus 1. All right. What does this behave like now? 0 over, well, 0. I get 0 over 0 again, right? What do? Panic. There's no answer. No, we don't panic. We just realize, let's do a L'Hopital's again. Derivative of the top is 1. Derivative of the bottom, product rule here, it's ln x plus 1 plus 1. Think about it. I did the product rule here. Right. Now the numerator is 1. There's no way I'm going to end up in a L'Hopital situation. What about the denominator? As x approaches 1, the logarithm is going to approach 0. It turns out the answer is a half of all things. Yeah, the answer to this limit is a half. So we started out like that. With two separate fractions, infinity minus infinity. I am making no judgments at this point because that is an indeterminate form. It is presumptuous of me to think that I know how it's going to turn out. Therefore, I need to rewrite it. Combining into one big fraction seems hopeful because L'Hopital's rule applies to a division of fractions. And L'Hopital's rule is something that comes to mind once I know I'm looking at an indeterminate form. So I do that. Then turns out L'Hopital's rule did apply. I get 0 over 0. So I did the derivative of top, divide by derivative of the bottom. Simplified very quickly. I got 0 over 0 again. L'Hopital's again. Now I end up in a situation where I don't need L'Hopital's rule. So this problem required two applications of L'Hopital's rule. simplification in between to make sure I know that. And then, yeah, we ultimately get to the answer, which is a half. So yeah, not going to start the second topic today, obviously. Interesting. I was going to introduce the main formula for the next section, but because of technical difficulties kind of slowed me down. Let's actually just stop there. So we'll pick up with that tomorrow. Tomorrow we will cover the topics of linear approximation and indeterminate forms. And marginal functions. Indeterminate forms is what we just spoke about. So yeah, that's it. Thank you for your time and attention. Hopefully that was helpful. And I will see you guys tomorrow in the next one. Ciao.